Okay, so we're going to start off week 5 by talking about oxygen and carbon dioxide transport. This should be mostly review, but there's going to be a few new things for you. Here are the objectives that we're going to talk about today. I know many of you are hoping that I talk about mean girls since we're talking about the oxyhemoglobin curve, but we won't. And for some of you, you'll have no idea what I'm talking about. So if you haven't heard this, I'm more than willing to share with you later. So when it comes to oxygen, there's two main ways that it's transported throughout the body. That would be bound to hemoglobin and dissolved in plasma. Okay, so like a huge majority is bound to hemoglobin. And so we want to make sure that we maximize what is on our hemoglobin. And so this leads us to the oxyhemoglobin dissociation curve. All right, on the x-axis we have pressure, and on the y-axis we have saturation. So saturation here, pressure is here. Okay, and so pressure, this is the plasma, and then the saturation, sorry, I know this is terrible, I really need to figure out a different way to do this, but that's the hemoglobin. Okay, so we're mostly concerned with what's going on here. Now, as it says here, we can shift this curve either to the left or to the right, and the nice thing is if we shift it to the left, we're decreasing certain variables. If we shift it to the right, we're increasing certain variables. Okay, and with the left shift, we're increasing the affinity, or in other words, we're increasing the attraction between hemoglobin and oxygen. If it's a right shift, we're decreasing that affinity. Now, just to be clear, normally our pressure is about 100, so that's here, which is about a saturation of 97%. Okay, I can't draw a straight line with this, but that's where it's at. Okay, and so we're actually never 100% saturated. It's virtually impossible to do, in large part due to the fact that we've got carbon monoxide and other stuff floating around in the environment. So with these left shifts and these right shifts, or just these shifts, okay, we decrease acidity, temperature, carbon dioxide. That's going to make it easier for oxygen to bind to hemoglobin. And the reason for that is that acidity is a measure of hydrogen ion concentration. And carbon dioxide is also a molecule. So if those two things, either of those two things are bound to hemoglobin, well, that's one less spot for oxygen, and then vice versa. Temperature changes kind of the structure a little bit of hemoglobin and just makes it easier for hemoglobin and oxygen to get together. So if we have low temperature, and then the reverse is true if we have a right shift. Now, what's interesting to note is that we have we can shift these curves, like I said, and we have names for these as well. So we've got the Bohr effect, which is when we have a reduction in affinity due to carbon dioxide. So if I've got lots of carbon dioxide, I'm going to reduce the affinity, and this occurs in the tissues, which is great because I want to get rid of oxygen and I want to take up the CO2. Then we've got the Haldane effect, which is essentially the opposite. We've got low CO2, and so as a result, it's easier for oxygen to bind, and we'll have that increased affinity. This occurs in the lungs. Now, I've got one more equation for you here that you may or may not have to use. I'm leaning towards not, but I'll give you more information when we get to this point. But the first one is oxygen carrying capacity. And so in order to determine capacity, which is the maximum amount of oxygen that can be held in the bloodstream, we need to know two things. We need to know basically how much is bound to hemoglobin and how much is dissolved in plasma. Okay, and so these two things, the hemoglobin and the saturation, go together, whereas the partial pressure is kind of separate from all of them. Okay, so these two go together, and then this is its own thing. All right, and so the equation is as follows. Okay, 1.34 milliliters of oxygen per gram of hemoglobin. Okay, and that's how much oxygen can bind. Times the concentration of hemoglobin. So how much hemoglobin is found in a deciliter of blood. It's weird units, but that's what we've got. Multiplied by the saturation plus 0.003 times the partial pressure of oxygen. Now, if we're looking at capacity, saturation will be 100%. If saturation is not 100%, which will never happen, then we're just looking at content, which is the exact same thing, but we've got a different saturation. Okay, and so in this case, we've lowered our saturation to 98%, and as a result, we have 20 mils of oxygen per deciliter of blood. Okay, so also important to note that women and people with sickle cell likely have lower hemoglobin concentrations, and so they might be affected during intense aerobic activities, meaning their performance will be decreased. I forgot we have one more equation. This one's pretty straightforward, and this is just how much oxygen are we delivering? And that's content times cardiac output. So just to make the math easy for our little example here, we'll say we have 20 milliliters of oxygen per deciliter of blood, and our cardiac output is 5 liters of blood per minute. Well, that turns into 200 milliliters of oxygen per liter of blood. Doesn't change it, just so we have the same units. So we end up with 1,000 milliliters of oxygen per minute, or in other words, 1 liter of oxygen per minute. To put this in perspective, you use about a half liter of oxygen per minute just at rest, and so you've got more than enough that you're able to deliver. Now, if you multiply this by 5, so like intense exercise, you have high cardiac output, that means you'd be able to deliver about 5 liters of oxygen per minute, which is quite a bit. So we're going to finish with carbon dioxide here, and so there are 3 ways that we transport that. It's either through bicarb, dissolved in plasma, or bound to hemoglobin. Most of it's dissolved as bicarbonate because if it's as bicarbonate, then it's not attached to hemoglobin. And this comes back to this equation that many of you have seen. So carbon dioxide, when it combines with water, with the help of an enzyme called carbonic anhydrase, turns into carbonic acid. It's one of the things that's in soda. It's what causes acid rain, that sort of thing, because carbon dioxide is a weak acid. That can then break down into hydrogen ion and bicarbonate. Now, when we're in the tissues, we want the equation to go this way, so to the bicarb, so we have less CO2 binding to hemoglobin. And if we're in the lungs, in the alveoli, where we're trying to get rid of CO2, we want the equation to shift this way so we can exhale the CO2. It's also important to know we use this for acid-base balance. Okay, CO2 is an acid, bicarb is alkaline, and so we will shift this equation depending on our pH. Okay, so if our pH is greater than 7.45, we're going to shift it to the left. Okay, we're going to try and produce more acid to lower pH. But if our pH is acidic, we've got 7.35, we're going to try and take that CO2 and form bicarbonate, which will help us make more acidic. Some of you might be wondering, well, we're producing hydrogen ion. That's correct. If we hold on to bicarb, we actually get rid of hydrogen ion. And this relates to something called the ventilatory threshold that we'll talk about later in the semester. And that's where we're going to end for right now.